Okay, so this is absolutely it as far as our discussion on polynomials. We're going to do an example of the things that we talked about in the last video. So if you haven't watched that previous video where we talk about end behavior, make sure you do that. But at this point, you should know how to find x-intercepts. You should know how to find y-intercepts. And you should be able to recognize the kind of end behavior. In other words, what's the polynomial doing as you go off the edges of the graph? The kind of end behavior that the function has. So with those three things in mind, we're going to work through an example together real quick. As you look at our learning objectives for this video, they are the learning objectives from the last video. Okay, be able to find those things and then sketch a possible graph. The last video was where we developed this rule. We talked about where it comes from. Again, if you haven't watched that video yet, you may want to go back to. So here's the example we're going to do in this video. We're going to find the x and the y-intercepts and then sketch a possible graph. Now, to find the possible graph, you're going to also have to find the end behavior. Otherwise, you got a 50-50 chance of making an impossible graph. Okay, so we don't want that. So you're going to need to find the end behavior, even though the directions don't explicitly say that. Anytime you're making a graph, you need to just know I have to find the end behavior. Okay, that's something that you need to recognize. All right, so with that said, let's get started. Personally, I like to find the y-intercepts first because they tend to be the easiest thing to find. So I'm going to say step number one, let's find the y-intercept. Okay, we've said previously, as we've talked about other functions, that every polynomial function will always have exactly one y-intercept. Now, don't misunderstand, there are some functions that don't have y-intercepts, but not polynomials. Whether it's a line, a parabola, a cubic, or other, any polynomial will always have a y-intercept. And we know that the way that we find that is we plug in 0 for x, right? We figure out what is f of 0. That's what we do. We plug in 0 for x. That's the way we find that. Now, based on our little trick, our little shortcut, notice right here, if I plug in 0 for x, what's going to happen is all of the terms are going to cancel out, because when you square or cube 0, you get 0. When you multiply things by 0, you get 0. When you add and subtract things with 0, you just get the other thing. And so that ends up being our answer. It just ends up being the number that was at the end. Okay. Now, that is still a valid trick that we talked about both with lines and parabolas. That trick still works. However, I want to caution you, don't forget that where that trick is coming from is that you're plugging in 0 for x, because just suppose for a moment that we wrote a function and it was not in its simplified standard function form like this. In other words, what if it still had parentheses? What if combined, and what if like terms hadn't been combined yet? Things like that. The number at the end might be deceptive. So just remember that where this is coming from is from plugging 0 in for x. That's where that comes from. So there's our step one. The y-intercept, therefore, the little 3 dots, that means therefore. Therefore, the y-intercept is when x equals 0, y equals 6. And there we have it. So there's our first step. I always do that first. Now, of the 3 parts that we're finding, the x-intercepts, the y-intercepts, and the end behavior, I typically do x-intercepts next. Even though it's usually the hardest, I typically do that next. And I'll be honest, the reason why I do that one next is just because I typically forget about end behavior until the time comes to actually draw the graph. And then I'm like, oh yeah, I need to know what's going on at the end. So I usually do the x-intercepts next. And we know for x-intercepts, what we do is we set y, or in this case, f of x, equal to 0. So instead of plugging in 0 for x, we're plugging in 0 for f of x. And then we solve this equation. So if we think back to the previous stuff we've done this week, I need to recognize how to solve that, which means I need to find how many terms it has and then determine the appropriate procedure to solve. So since that's something that you should theoretically know how to do at this point, why don't you pause the video and give that a try on your own? Once you've got it done, resume the video and we'll see if we end up with the same answers or not. All right, so hopefully you have found the x-intercepts and right now you're just checking your work. The first thing you should have done is look to see if there's a greatest common factor that these all have in common. And remember, there's 3 parts to the greatest common factor. I want the first term to be positive. If it's not positive, I'm going to make my greatest common factor a negative. Well, the first term is already positive, so I'm good. Then I want to see, is there a number that divides into everything? And in this case, because there's a 1 right there, the only number that divides into everything is 1, and that doesn't help me. And then the last thing I want to check and see is, do all the terms have a variable in common? And 3 of the terms have an x, but this one doesn't. So bottom line, there's no greatest common factor. We always check that one first. This one doesn't have one. Okay, so that's fine. Now we move on to what other method could I use? Well, it has 4 terms. And the only method that we've learned to do with 4 terms is the short kind of grouping, the kind where we already have 4 terms, so we don't have to invent more terms. Okay, so 4-term grouping, that's the nice kind. We just jump right in to breaking this up into 2 groups. Group number 1, group number 2. In group number 1, we're going to find the greatest common factor. So if we ignore all this other stuff, there is a greatest common factor, right? Both of these numbers, 4 and 24, they can both be divided by 4. And both terms have a variable. They both have x's. So I am definitely going to have a greatest common factor. Now, I need to verify, though, for my x, what should the exponent be? We've said all along your exponent is just going to be whatever the smallest exponent is. So when I'm looking at just these 2 terms, the smallest exponent is a 2, right? So then I go through this like backwards distribution process. If I were to distribute a 4x squared into a parentheses, I know there's going to be 2 terms here because that's how many terms that we end up with. 4x squared times what gives me 4x cubed? Well, that's 4x times x, right? And a 4x squared times what gives me negative 24x squared? Well, that's going to be a negative 6. So there's my parentheses. Now, for the second group, we said we had a shortcut. The shortcut was that the parentheses will have to match. So if this is x minus 6, this one's going to be x minus 6 as well. And now I can just divide a positive 6 divided by a negative 6. That's what I must have pulled out. So positive 6 divided by negative 6, that's negative 1. So that must be the number that was factored out. All right. So that tells me that my factorization after I'm done with grouping are the bits that are different multiplied by the bits that are the same. And so there is my factoring answer. Okay, now at this point, for my x-intercepts, I could set both of those equal to 0 and solve, and I would be good. And this is something that we have talked about solving, and you can do that if you want to. There's nothing wrong with it. It's okay to solve this right now by setting it equal to 0 and doing your math. But you can also recognize that this could factor more, right? 4x squared, those are all squares. 1 is a perfect square, right? 1 times 1 equals 1. There's 2 terms. They're being subtracted. So I could use my shortcut for difference of squares. And so since we're really focusing on reviewing factoring in this unit, that's the option that I'm going to pick. But if you would rather just set 4x squared minus 1 equal to 0 and then solve it, you should get the same answer. Okay, so if I factor, remember the stuff that's not part of the factoring process, that stuff all stays the same. That doesn't go anywhere. The piece that I'm factoring, though, the way it factors with our difference of squares shortcut is we write down 2 sets of parentheses. In the first one, we put a plus sign, and in the second one, we put a minus sign. And then we just take square roots. So to get the thing that goes in front, I'm going to take the square root of the thing that's in front. So the square root of 4 is 2, and the square root of x squared is x. So that's what's going in the front. And then for the stuff that goes in the back, I take the square root of the thing that's in the back. So the square root of 1 is 1. And so there is my complete factorization. Once I get a complete factorization, I set each of those equal to 0, and I solve. And then at that point, I will have my x-intercepts. So in this case, for my first factor, if I set that equal to 0, I'll subtract 1 from both sides. Since I'm running out of room, I'm just going to say what I'm doing and write down the answer. I hope you don't mind that I'm not showing work there. And then I'm going to divide both sides by 2. So we get x equals a -1/2. For the next part, same thing, except I have to start by adding 1 to both sides, and then divide both sides by 2. And I get x equals a +1/2. So -1/2, +1/2. And on the last one, I just need to add x to both sides. I'm sorry, add 6 to both sides. So I get x equals 6. So what are my x-intercepts? Therefore, the x-intercepts sorry about that, are when x is -1/2, y is 0. When x is +1/2, y is 0. And when x is 6, y is 0. Because all of these came from setting our y value to be 0. All right, so there I have all my intercepts. I'm pretty much ready to start making the graph. So on another page, a fresh page here, I'm going to go ahead and start with my axes. Make sure that we've got some good axes here. I'm going to switch to a marker, make my axes a little thicker. Okay, obviously you don't have to do that, but whatever. All right, so here is my y-axis, and now for the x-axis. Should have grabbed a ruler. That's not a very straight line, but that's okay. We all know what's going on. All right, so let's plot the points that we know. I know that my y-intercept is 0, 6. So x equals 0, y equals 6. 1, 2, 3, 4, 5, 6. There's my y-intercept. Okay. Next thing I know is that I've got x-intercepts at -1/2, +1/2, and 6. So -1/2 over here, +1/2 over there, and then 6. 1, 2, 3, 4, 5, 6. There. Okay. So obviously I'm counting by ones on this graph. It's a good idea to label those. Not always 100% necessary. Depends on what your teacher wants. For me, I pretty much say absolutely label them if you're not counting by ones. But if you're counting by ones, I'm okay. All right. Now, the last part is I know I'm going to connect those dots with a curve. Okay, some smooth curve that's going to connect all those dots together. But is my graph, I'm going to use a highlighter so that it's not, dark and permanent. We can draw the actual graph and know for sure. Is my graph going to end up, what I don't know right now, well, I guess I kind of know, right? If I'm going to connect these dots together, I've got to do something like this, right? Something like this, okay? Give or take, something like that. But let's check our end behavior. Does that match what we know? Does that match what we know? We have said that if the leading term is positive, which ours is, then on the right-hand side, the graph should be going up. Is my right-hand side going up? Yeah, it is. Perfect. Okay. And we've also said that if the degree of the polynomial, the biggest exponent, if the degree of the polynomial is odd, the left-hand side should be doing the opposite. So this was going up. This one should be going down. Oh, yeah. Yeah, it is. Okay. So in this case, we almost didn't even have to figure out end behavior. Just connecting the dots in a logical way got us what we need. Okay. So that's our graph. Connect our dots together in a logical way. Ooh, I sort of missed that graph. Ah. Okay, functions will never bend backwards like that. So this is a terrible graph. I apologize. But it gives us the basic idea. This should just go straight up to there. That's what it should do. Okay, that's a better graph. That's a little bit better graph. Okay. And you should know, right, because we've talked about this, you should know why a function can't bend back like that. Okay, so if you think about that, you should know, right? Vertical line test, hint, hint. All right, so there we go. There is our graph. So ignore this little piece over here. There's our graph. All right, now the last thing I want to mention is, remember I said you don't need to understand or be able to graph the exact right stuff for the squiggles, that we are just focusing on getting a possible graph. So what do I mean by that? Well, notice that my yellow squiggle and my black squiggle don't exactly match. we don't know what this squiggle is doing. We're not at that level of math yet, okay? So maybe this goes like way down and back up. I don't know, right? We don't currently, with what we know about math, we don't know exactly what that squiggle does. You have to know a different kind of math called calculus to figure out exactly what is the bottom of that valley. How low does it go? And we don't know calculus. We're just learning algebra. So when you make your graphs, do not get stressed about these squiggly parts. As long as you hit all your intercepts, and as long as you have the right end behavior, you're going to get full credit for your graph. All right, so that takes care of our example. Hopefully you're comfortable with that material. Obviously, if you've got worries, concerns, shoot me an email, let me know, and I'll try to help. Thanks for watching. Have a good one.